Sravyasri Garapati is currently a senior machine learning engineer associated with Intuit, holding a bachelor's and master's degree from IIIT Hyderabad with a focus on multi-agent systems. Shravya is deeply passionate about applied machine learning. She is driven by her vision of democratizing AI and Gen AI solutions, palpable in her efforts towards constructing reusable services in this realm. Damitri Kundu is currently a senior data scientist at Intuit. She holds a PhD in statistics from the Indian Statistical Institute, Kolkata. Her research involves studying the association between biomarkers and time of relapse for children suffering from leukemia. She co-authored 7 publications in journals like SMA, J Biopharmstat, Lifetime Data Analysis, etc. Her area of interests are machine learning, Bayesian modeling, and causal modeling. Warmly welcoming Shravya and Damitri for this.
Hope I'm audible. Yeah, super. Hope all of you are having a great time at WITS. Happy to see all the faces and glad to have this opportunity. So, yeah, this session will be covering automatic prompt optimization in large language models. And just to quickly introduce myself, I'm Shravya, Senior Machine Learning Engineer at Intuit. Yeah, so by the end of this session, I hope everyone will take away how to optimize performance of LLMs and why right instructions are really important for LLMs, and also automatic prompt optimization, along with optimizing few short examples, which my colleague Damitri will cover, both based on questions and skills. Yeah. So I won't bore you by going and telling you all about large language models. So I just want to say large language models are language models which are trained on large amounts of data. Say, for example, GPT-3 is trained on about 45 terabytes of data, and it has about 175 parameters. What it means that they're really effective and can do things for you, right? And in the past year or so, we have seen that they have fueled a lot of innovations, and there is definitely an ROI learning about LLMs. So let's look at how we can maximize the performance of LLMs, right? Depending on the problem you solve, we can, it looks something like this, wherein, you have two axes here, what the model needs to know and how the model needs to act, right? So a typical flow would look like you start with instructions, you do prompt engineering, you quickly look at what the model needs to know or how the model needs to act, and you add examples. And then, if you have large enough corpus, you add retrieval there, where, that comes into picture. And if you want the model to follow instructions, that's when you go to fine tuning. So if you look at it, right, RAG and fine tuning, it's not like either or one or two of them. They are additive. They can stack together depending on the use case you're solving, right? So yeah, again, depending on the use case, it can be one of these, two of these, or all of these. So, and prompt engineering would be like the best place to start, and it can be the best place to end as well. So for some use cases, you might just need prompt engineering and it would do wonderfully well. So a typical prompt would have two sections. One is the instructions, the other one is the examples. So instructions should be articulated really well to get the most out of LLMs. So for example, please consider each step comprehensively before giving your answer, or like think carefully and answer, right? And then examples can look something like this, wherein, these are the inputs, these are the outputs, and you can stack multiple examples to make LLM know better. And the best way would be to have clear instructions and also have meaningful examples. Now that we just discussed that articulating instructions is really important for LLMs. And why is it so? For example, this is a classic case of prompt sensitivity, wherein two semantically similar prompts, which are kind of telling the same, but the outputs are different and the accuracies are different. And this is a case with GPT-4, which is a sort of state-of-the-art LLM, right? And the way you prompt. So if you look at this example, there is a standard prompting versus chain of thought prompting. Chain of thought prompting is where you ask the LLM to think in a chain and answer well, right? And if you look at the answers, the standard prompt led to a wrong answer, whereas if you put the same prompt in a chain of thought prompting pattern, it gives a correct answer. So that clearly shows how important, the way you write the prompt matters, right? And then an interesting thing, prompt ambiguity, right? So if you look at this example, we have a prompt which says assess whether the message contains advertising. If it is advertising, answer yes. If not, answer no. A simple classification problem, right? And the message says, I recently purchased a dress from your store. Now, I also found a similar one at a competitor's store. Now, could you match the price? And the LLM, rightly so, has predicted it to be not an advertising message, right? But as a use case administrator, I might want it to be an S because there is a competitor's name mentioned in the message, which means the competitor is getting an advertisement there. So it really depends on the intent of the use case administrator here. And it's really important to add intent to the prompt. So that's where you have to have a clear prompt which will not be sensitive, which is not ambiguous, and which has like the standard prompting patterns. Say suppose you have all of this and you furnished a great prompt. So it need not say it works well with GPT-4, say. It need not work with a different LLM, say Llama, right? And if you furnish a prompt for, say, Llama, it need not work for GPT-3, right? So it's really important to have a prompt optimization pipeline. So given your use case, given your benchmark details, and given your expectations, the intent, you need an automatic pipeline which can furnish you the best prompt that can give you the best accuracy, and it should be automated. Be it any LLM, it should be able to figure out what works best for that particular LLM. Yeah. So can we optimize prompts automatically? Right now, there has been some literature around this area, and we'll focus mostly around using LLMs to optimize the prompt. So we describe the prompt optimization problem in a natural language and ask LLM to iteratively optimize the prompt based on the historical prompts and their performance. Also, of course, we need to give the task description. And any optimization problem, we need to have a valid benchmark here with respect to LLMs, right? So you need to have a benchmark with all the cases covered to figure out how good the optimized prompt looks like. Yep. So I just said LLMs can be optimizers. So yeah. So there has been some research around using LLMs as optimizers and if they would be a good optimizer. This is the work from DeepMind, and they try to use LLMs to optimize coefficients for linear regression. And interestingly enough, LLMs are good black box optimizers for small scale problems. Of course, they can't surpass a gradient descent, which is state of the art optimization algorithm, or like a custom solver, right? But they are at a small scale, they are pretty good optimizers. So if you look at this slide, the first row, it depicts that GPT-4 took 17 steps to achieve global optima in a linear regression use case, right? So we take this as a premise. We use LLMs to optimize the prompts, and let's see how we do it. So this is the workflow where we use LLMs to optimize the prompts. Of course, I'll also show a use case and an example of this working in real world. So we start with the task description and the initial prompt. So, and then we generate the boundary cases, adverse examples, like the ones that we saw in task ambiguity, right? Prompt ambiguity, sorry. So these are those boundary cases wherein you really want the user intent to come into picture. And these can be generated by an LLM, a state-of-the-art LLM, or can be a human generated or human annotated, right? And then tag those examples. Again, it can be a human or an LLM doing it. Once the examples are tagged, you have the You have the examples, you have the tagged annotations. Now you use these examples to predict using an LLM, right? So now you have y prediction, y predicted, and you have y actual. So you can easily do an error analysis here and evaluate what has missed and what are the misclassified samples for a classification task, of course. And then this error analysis is sent to an LLM, which is again the optimizer LLM, to generate the new prompt. And this iteratively happens, and the LLM clearly is an optimizer here, which is getting all the past scores along with the task description, along with the prompts that were tried. So we asked the LLM to give a new prompt which is better than the previous prompts for this particular use case. Right. So I'll demonstrate a use case. Yep. So we'll try automatic prompt optimization for this particular use case, wherein we ask LLM to classify whether a movie review has a spoiler or not. Right. So we define the task. We say, assistant is an expert classifier that will classify a movie review and let us know if it contains a spoiler or not. Right, a simple classification task. And we'll iterate through one iteration and see how the prompt gets transformed and how the accuracy numbers change. And this is the initial prompt I have come up with. Does this movie review contain a spoiler? Answer yes or no, right? And this is the meta prompt. So generating boundary cases, here I have used LLM. Of course, we can generate by a human. It can be generated by a human as well. So if you look at the prompt that I have given, these are called meta prompts, the ones that we use for optimization, generation, and error analysis. So this is one of the meta prompts that I have, which says, the generated samples must be challenging and diverse. And also they should be equally balanced between the classes. Since for example, here it should be yes or no, right? And the samples must be equally distributed between them. And they should be distinct, realistic, and, they should vary significantly because all the challenging prompts should not be saying the same. And I'm generating 5 prompts for simplicity. Of course, you can generate how many ever you prompts, not prompts, the samples, and we can work on them. And now I use a state-of-the-art LLM for sample generation. So I give this meta prompt, you generate me all these boundary cases where this task can go rogue or this task can go ambiguous, right? And let's look at the samples generated by the LLM. Here I use GPT-4 to generate the samples. And if you look at this, these are really interesting samples. And if you look at the second one, right, the movie was a roller coaster of emotions. The scene where the main character's past was revealed was heart-wrenching. I won't spoil it for you, but it's a must-watch. So you get the point, right? These are really, like, you need to put it in the prompt saying it might reveal some scenes, but it will not reveal the spoiler. So these are the boundary cases that it generated. And here I'm annotating them manually. And this is what the annotation looks like. And if you look at now that we have the boundary samples, I use the LLM that I want to put in production to predict for those boundary samples. So if you look at it, these are the predictions that we have gotten from the LLM that we want to use for this particular task. Right now I have used GPT-3.5 Turbo, and yeah, it has gone wrong at few places, of course. Now we have the annotated prediction and annotated labels and the predicted labels. So it's easy to analyze the errors, right? A classic machine learning example, like, you get the accuracy score, you get the confusion matrix. And if you look at it, the accuracy score right now is 40%. Of course, the data set is pretty small, but let's see how it goes, right? And I also identify the failure cases where it has gone wrong and mislabeled, right? These are the cases where, you see that the LLM has mislabeled an S to be a no or a no to be an S. Now, these errors and the accuracy score, confusion matrix, and the misclassified labels is given to a state-of-the-art LLM, which is right now I'm using GPT-4, where I'll tell, the analysis should, you do an error analysis on these misclassified labels. You have the accuracy score, you have the confusion matrix. Now you tell me what is the, where did the LLM go wrong? Where were the mistakes? And, you make it crisp, you make it like below 200 token. Tell me what the issue is, right? So if you look at the error analysis, it's amazing. See, the common failure cases, if you look at the second paragraph, it says the common failure cases involve reviews that hint at significant events or scenes in the movie, but does not explicitly reveal the crucial plot. So it is misinterpreting these hints and building up as a spoilers, right? Now that we have the error analysis in place, and we have the misclassified ones, we ask the optimization or optimizer LLM. So this is the third time we are calling the SOTA LLM, which is again GPT-4, to say, this is the task description and this is the previous prompt. And here is the error analysis for the previous prompt that we just tried. Now give me a new prompt, which is different from the prompt that I had given above, and also incorporate this error analysis in the prompt that is coming up. So it must adhere to the error analysis instructions, and it should be, taking into account the accuracy score and the other details that are given. If you look at the new optimized prompt, right, you see that it has improved significantly given the samples that it has misclassified. So please classify this movie review based on whether it explicitly reveals crucial plot details or not, right? If it does, answer is. If it only mentions scenes without revealing key plot twists, answer no. And let's try this new prompt on the same samples and see how it goes. So I've, So this is the initial prediction, and this is the prediction after the refined prompt. We'll use the new prompt on the same samples to see how it goes. And again, I calculate the accuracy and I see it has improved to 60% from 40%. And this is just one iteration. And I have taken very few samples for simplicity, right? So there is potential in having an automated prompt optimization pipeline at any place that we work. And we see clear results using LLMs as optimizers here. Hope this helps. And of course, we can extend this to generation tasks as well, wherein we modify generation task to a ranking task. So you ask the LLM to generate particular content and you rank it, say 1 to 5, right? And then it becomes a classification task again. So this can be ported to generation task as well. Yeah. So that's pretty much what I have. Hope this helps. I'll take the questions once my colleague is done. So Damitri will now cover how we can optimize the few short examples in the prompt. So yeah, yep. Sorry.
Yeah. Yes. It's this one, right? Sravya, this one, right? Okay. Yes. Now I will cover as the parts where you can improve a prompt by adding a few short examples. So these can be there can be two methods to do that. One is the raw query based, and one is the skill based. And it is observed that the order in which the few short examples are placed in the are also have an effect on the final accuracy of the predictions by the LLM. So we start with the raw query based techniques. One of them is called KATE, which is the KNN augmented text in context example selection, wherein you have a lot of training examples and you select only a few of them in your and you select a few of them for your in context, and within that you select the ones that are most closest to the query that you've set. So the red dots are the nearest neighbor. The gray dots are the ones that are selected from the training samples, and the white ones are the unused samples. As you can see here. So
here in the training data, there can be, in this training data, you can see that there is a county of, I can't see. So there's a county of Duluth, Minnesota, and what is the Olympic athlete has won the most medals. So these are all sorts of the prompts in all sorts of questions in the training data set, out of which it selects the K most closest neighbor, where the actual question was what county is Frederick MD or in. So these are the questions in the K nearest neighbor, which are fed into the GPT-3, and the GPT-3 gives the answers. Here's an overall algorithm of that. So you have the test questions. What happens is the prompt, and we take the queries which are closest to the test questions in the entire training data set. And how do we do that? We first convert all of the queries to their embeddings given by mu theta, and then we then we also convert the query in question, the query that you want to make in the embedding format, and then we see that its closeness with respect to negative L2 norm or their cosine similarities. Based on this similarity, we select the K nearest question, and now we have, suppose we have selected the K nearest questions and answers. The answers would be the Y denoted by YIs, and the X would be the queries. Now, all of these K questions and answers are in the context C. They are fed with the actual question to the GPT-3 to get the estimates. And we see, and this actually beats the random method where we randomly select certain examples from the training data set and try to make that context C. So we can see in the table that the accuracy of the random is the least for the Kate and several other versions of Kate with different embedding settings, the accuracy gets higher. So Kate Roberta means the embeddings used here, mu theta, is Roberta, and for NLI, it is the Kate underscore NLI, meaning that the embeddings here used is that mu theta is the embedding which is trained upon the NLI data set, and similarly NLI plus STSB, which is the semantic text similarity benchmark data set, and the last one is the SST2, which has the highest accuracy. It is because this Y test is based, the test data is based on IMDb reviews, and it's based on a sentiment analysis of these reviews. And SST2 is a data set by Stanford where they train the embeddings on movie reviews, which is why it gives the highest accuracy. Yes. So these are some of the in-context examples and the predictions. As we can, let us take the first one. The question is the Mughal gardens of the Rashtrapati Bhavan is modeled in which garden? Modeled in which garden? Yes. So the Mughal garden of the Rashtrapati Bhavan is modeled by the Persian-style gardens, Persian architecture. Who built them? And these are some of the, as you can see, the in-context examples are drawn based on the query in question, which is the where we see semantic similarities with the questions like the Mughal gardens or the model or the garden itself, and you can see all of the in-context questions to be on that format. And the ground truth is here is a Persian garden, as you can see from the very first question and answer. The answers would be in the underline, and Kate responds as the Persian garden. But in random baselines, which can concern other sentences such as which include Shalimar Gardens or some architectural techniques that involves Shalimar Gardens, would give some random baseline in Shalimar Gardens. So which is here Kate differs from the random baseline. So that is why we prefer Kate. Now, this is a completely non-parametric technique as we are using KNN, so no parameters are involved except for the embeddings. And here, as you can see, as you have seen in the previous slide, that it has exceeded or outperformed the random sampling techniques. But the main problem with the Kate is that it heavily depends on the embeddings that we use for the model. So for embeddings that we use for embedding the sentences. So like we have used Roberta, or as we moved to better embeddings with built on better data sets, the accuracy went up and down. So this is heavily dependent on the embeddings, which is why we move on to skill-based KNN, which is based on the skills. So suppose your input query is which cities do more than one employee under the age of 30 come from, and suppose the in context examples are in which city do the most employees live and how many live there. As you can see, these are task based questions, and seeking semantic similarity between the questions will not lead to a good answer, which is what would it do, which is what we refer to as a raw input based selection technique. Here we are more interested in the skills. So the skills that we require for checking the input query is we first have to select employees under the age of 30, and then select cities that have more than one. So first select cities that have more than one employee and age 30. So there are a couple of tasks that are in place, like there is a more greater than and less than operation that needs to be done, which cannot be understood from the semantics just themselves, which is why we refer to the skill-based description. Now, suppose you have a DB schema which containing the name, age, city, etc. And the question is which cities do more than one employee under the age of 30 come from. Now, we break down that into several tasks and as candidate descriptions. So suppose one of the candidate description is the task requires a greater than and less than constraint. And then the task requires to apply 2 constraints on one column, and etc. So we have several such candidate descriptions. These are then converted to the some off-the-shelf embedding, just we saw in Robot or SBot, and then whatever was in the question banks, whatever questions and answers were there, they are all converted to such candidate descriptions and then converted to their embeddings. And now we can map these embeddings together, and we can map the similarities between the embeddings and see which question which questions in the context are nearest to the query that we are asking. And hence we can get this data set was built on an then the context would give an SQL based query, and then since the context contains a SQL based query, it will give you a reply with an SQL based query, which upon further hitting the API will give you a result. So like some number based on the database that is hitting. So suppose here is another like comparison between CATE and skill KNN. So suppose what is the most preferred method of payment for working professionals in Manhattan? Say that the ground truth is credit card. Now, now we have a query, what is the most preferred method of payment for working professionals in Manhattan above the age of 30? See that between question 1 and query, you have several similarities like most preferred, working professionals, Manhattan. These are all similarities. So Kate will most probably just see the semantic similarities and extract the answer as credit card, which is wrong because it also includes a further condition called above the age of 30, which is where our skill KNN takes place. We convert them into candidate descriptions like candidate 1, candidate 2, form the SQL query, and then get the correct answer. And see in case of the second part, which is a query, we get the SQL query like this, and which also includes a condition age greater than 30 and gives us the right answer, debit card, which is why we use this technique. And so you will now automatically not have annotated descriptions for all of the queries in the question bank, which is why what you do is you first select a few questions from the training set, annotate them with respect to the descriptions, and then ask the LLM to generate descriptions for all of the questions. And then once you have the query to description mapping, you change that, embed those descriptions, and then you can do what you did for KNN mapping in case of Kate. This table over here shows so some of the annotated examples did not contain all examples of how the skills should be generated. this shows that even if you give input queries which require special conditions, the generated skill from the LLM will give you those special conditions, like apply the null constraint which were not present in the annotated versions of them, and finally will give you the SQL query. So these are some of the examples of that. And now the SQL query and skill KNN has two variants, and that will we need this because like in the previous previously I've said that the order in which we are giving the examples in the context also matters in what it predicts. So it also affects the accuracy, which is why we require these two cases, consistency based and distinctiveness based variants, where first we ETs are the EIs are the so suppose a query XT is broken down into descriptions S1T, S2T, SMT, which of which a grand set is known as the ST. Now we convert them into with embeddings, and then we see the similarity, that is the base model. But for consistency based, we check the mean embedding between these two queries, between the descriptions of these two queries, and this is useful when the order causes a zero mean distribution noise in the noise in the data, which can be resolved. But however, the overall context between both of these two, the overall meaning of both of these two descriptions are same, which is captured by the mean embedding, which is E bar over here, and that is how you compare both the a question from the question bank and a query. And in the distinctive based feature, we do not look at the central embedding, but we want to select the most distinctive characteristic of the descriptions, which is why we look at the maximum of the similarity between the embeddings. So as you can see in the right one, you can see the most nearest cases here, and in the left one we see the comparison over the mean. The distinctive based cases are mainly used for cases when there is a spike, or when there are trivial cases in the description which causes a very high embeddings with very high magnitudes, which then if you use consistency based cases will lead to higher distances, because means are often not robust enough to handle outliers, which is why we use this maximum similarity, which is where we are seeing the minimum distance between the two embeddings. And this is a comparison across for GPT 3.5 Turbo and GPT 4 for all of the methods, including random selection, to the KNN. The KNN one is the same as the KT one that we showed, and the skill-based SBUD were at base, as well as the consistency and distinctiveness variance. We can see that always the skill KNN on an average beats the random as well as the KNN versions, both in GPT 3.5 Turbo and GPT-4, especially in GPT-4. As you can see, the accuracies are quite different. And the highest accuracy was there for consistency, and here for distinctiveness. And this was done in a sentiment analysis for some SQL dataset with 7,000 examples. Now, this skill-based ANN does not require fine-tuning, which is one of the pros, because fine-tuning requires a lot of resource and time. And generating skills using and it also outperforms the raw input-based techniques. As we saw, it beat KT. But where it lacks is if the questions are not task-based, this is where skill KNN will not be of much use. This is one of the cons. So, and these are all the papers that we have referenced while making this. So that's it. Yeah.
Do we have any questions for the speakers? Okay, there's one. Can we get a floating mic?
Yeah, so You have given an example for, like, this is for you, like prompt optimization. So as we have seen that most of the industries are heavily having unsupervised data, and we in our organizations are more towards, let's say, computation and calculations, which today also most of the LLMs are not quite good at. So wanted to ask, like, the example also which you have given is more towards supervised, and we are inclined towards annotation, and the data which we deal with is kind of big data, for example. And even if we take some 5-10 examples, or let's say 100 examples, and annotate it and do this prompt optimization, do you think that would be viable to justify that it's going to give us the same prompt is going to give us the correct answer for the entire, let's say, the entire framework which we are building?
Yeah, so this translates to the classical machine learning problem, right? You have training data, you have test data, and if it works on test data, you go with the hope, and then you do an online continuous monitoring of the model that is put in production, right? So likewise, this of course translates to a supervised model wherein you have annotations and you have human annotations. If not, you ask an LLM to annotate it. But the crux is, you take that train test data, you evaluate, and then you do that continuously so that not to lose the track of models, right? That's where model drift comes into picture. You understand where the drift is happening and then quickly pivot based on the use case.
Yeah, just I have asked this query because I think that the entire prompt optimization which you explained can easily be solved using, we have this called as reflection, where we just simply say the LLM itself to check the answer which it is doing, and there are certain frameworks also, for example, DSPy and Langsmith, etc., which is currently doing this, though the backend might be whatever it is doing, but it's self-evaluating, right? So even, let's say, for example, if we are constructing this and we are making, let's say, for example, 4 LLM calls in a single cycle.
I would want to correct there. It's not self-evaluation, but we would use a better LLM. So we might not want to put GPT-4 in production because it's costly, right? So you use GPT-4 only during the initial phases of your prompt development, and then you go to a cheaper model in production, right? So you only use the SOTA LLMs for evaluation. It's not self-evaluating, but you use a different LLM and then learn through LLMs.
Okay.
Yeah. So it's, yeah.
Okay. Thank you.
Okay, any more questions? One there.
Hi, thank you for the lovely presentation. My name is Ruby. I came in a little late, but I wanted to know for the LLM model and the error example that you showed, did you have anything in terms of benchmarking or a success criteria? How would you know for every prompt answer that you get the inference, whether it's a false positive or a false, how did you evaluate that?
So the evaluation was clearly based on the annotations that humans has provided,
Okay,
right?
but there
And
was
we
no benchmark?
iteratively.
Any
No.
benchmarking?
So the one that I had presented, we did benchmark on the IMDb data,
Okay.
and we came up with about 90% accuracy on
Okay.
IMDb movie reviews.
Okay.
But the one that I had shown, it's an iterative process, right?
Mhm.
So you start with say 30 samples, and then you iteratively do it for about 25 steps by when you would have hit like 90% accuracy on your benchmark set. So
Okay.
yeah.
All
That's
right.
an idea.
The other question I had for you, in the visual that you showed there was a test prompt and there was training data. And in the later example, you showed ground truth. But I didn't see any validation test data set. Is that implicit or is that needs to be considered in your visual?
I showed two cases. Which one you talking about?
In that first visual diagram, there is a test input prompt and then
Yes.
there is a test training data. But I didn't
Yes.
see any validation data. So how are you validating for ground truth? I wanted to understand that.
So in the skill-based KNN, so I think the validation are done like for the ground truth, they are done manually because they are done for a very small amount of data. Is that what you're talking about?
But manually, for how many iterations you're going to
That was not mentioned actually in the paper.
All right. Okay. All right. Thank you. I found that as a small gap. That's the only reason I asked.
Got it.
Because we are trying to do something similar, and our challenge is how to incorporate ground truth as part of validation data. So I was looking for that anyway. Thank you.
So benchmark.
talking about the annotations, right? Login accuracy is based on the annotations, right? So the annotations, whoever it is doing, either it is human or LLM, or even using a machine learning, right? It's purely subjective, correct?
Exactly.
It's
That's what.
it's
yeah.
all based on the business understanding of
Yes.
it. If it is based on a new movie review, right? It's purely subjective. And for in case like for a retail store, there is a chatbot when we had started doing the annotation. So whole accuracy is based on their annotation.
Yeah.
Correct.
So it's best to have a business expert or the use case administrator.
Exactly.
To have it.
So even with that,
research.
right, annotations, we can like go with a clustering that or a classification combination of the ML, that is traditional overarching the traditional ML, then using the LLM. Will it be like a bring out the more accuracy?
So when you say clustering,
No, traditional ML, right? We were overarching the traditional ML into the LLM. So when we were doing the annotation itself, right? One more way of evaluating, one more layer of validation when we are doing the annotation itself, that will give us a better accuracy, isn't it?
can be doable.
I know it's a
Depends on
consequence.
the use
Yeah.
case, though.
Depends upon the use
Yeah,
case.
and the data
Consequence.
you have, how much data you have, right? Classical models need some good amount of data to be present. So, yeah. But that's a nice insight. Thanks.
Yes, thank you so much.
Okay. Do you want to take this question here or at the networking lunch?
Oh.
Whatever suits, but all right, we'll take this one and then we'll move on.
Hey Shravya, it was a good presentation. So I have a concern related to the fintech company. So a lot of information we have is very sensitive, and will the LLMs be able to protect that information even if the prompts are given in a indirect way?
So again, I can only answer if I get to know the use case. But at Intuit, we make sure that no sensitive data is sent to the LLM. We mask it before even sending it, right? So we have security risk fraud detection in place, which can mask the data or make new data which looks similar to the data that is by the users, but would not give out the identity, right? Those are some tricks we can do to incorporate sensitive information.
Or should we prepare our own LLMs instead of using GPT-4 giving the data there?
So, yeah, that's really subjective question.
All right, do we have any more questions? If at all, then you can connect with Damitri and Shravya in the networking lunch. We would like to present you with a token of appreciation. We would like to call upon Anusha Mujamdar, Senior Manager Data Science and AI at Intuit, to give these tokens of appreciation. Thank you. We now have a very special guest, our guest of honor, Aruna Rajan ma'am, Director of Machine Learning at Google. Aruna Rajan, she has her academic